In earlier video, we discussed about the electronic configuration of group 17 elements and some of the physical properties of group 17 elements like atomic and ionic radii, physical state, color, electronegativity, electron affinity, etc. Now next important property of halogens, or next point, is oxidation states of group 17 elements. So this is the electronic configuration of group 17 elements, valential electronic configuration. It is ns2np5, and from this electronic configuration it is clear that when halogens gain one electron, their octets will be completed, and therefore they have strong tendency to gain one electron, and because of this their common oxidation state is -1. In addition to -1 oxidation state, chlorine, bromine, iodine, these elements shows positive oxidation state also, that is +1, +3, +4 and +7. Chlorine and bromine shows +4 and +7 oxidation state in oxides and oxoacids, whereas fluorine shows only -1 oxidation state. Reason for this is in fluorine d orbital is absent and its electronegativity is very high, and because of this its common or its most stable or only oxidation state is -1. Now these various oxidation states of halogens like fluorine, chlorine, bromine, iodine, it is correlated with the electronic configuration of these halogens. Now this is the ground state electronic configuration of halogen. The configuration is ns2np5, and it requires only one electron to complete octet. In that case, when halogen gains one electron, its oxidation state will be -1. When we think about fluorine, in fluorine d orbital is not there, and therefore in fluorine there is only one unpaired electron. Its covalency is 1, as well as its oxidation state is also -1. As promotion of electron from p orbital to d orbital is not possible for fluorine, as d orbitals are absent, so promotion of electron from p orbital to d orbital is not possible for fluorine, and therefore fluorine cannot extend its valency beyond 1. Okay, for other halogens like chlorine, bromine, iodine, there is possibility of excitation of electron from p orbital to d orbital. Now when one of the electron from p orbital is excited to d orbital, then there will be 3 unpaired electrons, and in that case the covalency will be 3 and number of unpaired electrons are 3. Similarly, when 2 electrons are excited from p orbital to d orbital, total number of unpaired electrons will be 5, covalency will be 5, so 5 electrons can be shared with these unpaired electrons. In that case its valency will be 5. And when 3 electrons are promoted from lower energy level to higher energy level, one after the other, in that case altogether there are 7 unpaired electrons, and in this case the covalency will be 7, and excitation of electrons from lower energy level to higher energy level, it is possible for chlorine, bromine and iodine only, and not for fluorine, because in fluorine d orbitals are absent, and hence for chlorine, bromine and iodine valency can be extended from 1, so it can be +3, +5, +7. Okay, and in some cases for chlorine and bromine it is +4 and +6. Now next point is anomalous behavior of fluorine. So fluorine shows some unique properties or different than the chlorine, bromine and iodine, and it shows anomalous behavior. So as compared to other group members like chlorine, bromine, iodine, astatine, some properties of fluorine are different or unique, and therefore it shows anomalous behavior. And this anomalous behavior of fluorine, it is because of its too small size, high electronegativity. Electronegativity of fluorine is 4, and it is highest, or it is actually highest electronegativity among all the elements in periodic table. That is 118 elements in periodic table. 118 elements are there, but fluorine is having highest electronegativity. Even okay, and when we compare to group members, its electronegativity is highest. At the same time, in case of fluorine molecule, F2 molecule, the bond dissociation enthalpy is low. It means easily this fluorine bond can be broken, and F minus is available for reaction, and in fluorine d orbital is absent, and these are the reasons for anomalous behavior of fluorine than the rest of the elements. Now here ionization enthalpy and electronegativity values for fluorine are higher than expected. For other elements these values are low, whereas for fluorine this value is unexpectedly high. Ionic radii, boiling point, electron gain enthalpy, these values are lower than expected. For other elements these values are comparatively higher. So fluorine molecule, it is extremely reactive and reaction is exothermic, and reason for extreme reactivity of fluorine molecule is low bond dissociation energy, whereas other halogens, diatomic halogen molecules, they react, but they react less vigorously than the fluorine. Oxidation state of fluorine is only -1, whereas other halogens show positive oxidation state also, that is +1, +3, +5, +7, etc. But fluorine shows only -1 oxidation state. Hydrogen fluoride, that is hydride of this halogen. So hydrogen fluoride forms hydrogen bond. It is able to form hydrogen bond because of high electronegativity of fluorine, whereas other hydrogen halides like HCl, HBr, HI, they have a less tendency of formation of hydrogen bond, and this tendency is highest in hydrogen fluoride, and therefore it exists in liquid state. Because of hydrogen bond, HF exists in liquid state, and other hydrogen halides are gases. So fluorine, it is able to form ionic compounds, whereas the percentage of ionic character in other halogen compounds, it is less. Covalent characters are more in case of the compounds of chlorine, bromine and iodine, whereas fluorine forms the compound in which ionic characters are more. Hydrogen fluoride is liquid at room temperature. Already I said it is a weak acid because bond between hydrogen and fluorine is very strong, and therefore it is a weak acid. On the other hand, other hydrogen halides like HCl, HBr, HI, these are existing as gases at room temperature. Now, due to absence of d orbitals, hydrogen fluoride does not form, or fluorine does not form polyhalide ions, whereas other halogens, they form polyhalides like I3 minus, Br3 minus, I5 minus, etc. These are the polyhalides, but fluorine does not form polyhalide, and this is because of absence of d orbitals. And hydrogen fluoride cannot be stored in glass bottle. It reacts with sodium silicate, one of the important component of glass. Hydrogen fluoride reacts with sodium silicate, and there is a formation of sodium fluorosilicate, which is soluble in water, and therefore hydrogen fluoride cannot be stored in glass bottle, whereas other hydrogen halide solutions, these can be stored in bottle. For example, HCl, HBr, HI, their solutions can be stored in glass bottle. And these are the some unique properties of fluorine and its compounds, and therefore it shows anomalous behavior. Okay, now next point is chemical properties of group 17 elements. Now from fluorine to iodine, chemical reactivity gradually decreases. So fluorine, it is most reactive, iodine is the least reactive. Now first is reaction with metal and non-metal. So these halogens react with metal and non-metal and they form the halides. For example, fluorine react with copper and there is a formation of copper fluoride. Bromine react with aluminium and there is a formation of aluminium bromide which exists in dimeric state. Fluorine reacts with sulfur, that is non-metal, and forms sulfur hexafluoride. Chlorine reacts with sulfur and forms sulfur tetrachloride. Bromine reacts with sulfur and forms sulfur dibromide. So reactivity of halogen, that is fluorine, chlorine, bromine, decreases. Reactivity of these halogens with sulfur decreases. Fluorine forms hexahalide, chlorine forms tetrahalide, and bromine forms dihalide with sulfur, whereas iodine does not react with sulfur. Now reaction with water. Fluorine vigorously reacts with water and it oxidizes water into dioxygen or ozone. As soon as fluorine gas is passed through water, there is a evolution of oxygen gas and there is a formation of fluoride ions. Chlorine and bromine oxidizes water slowly in presence of light. Now reaction with hydrogen. All halogens react with hydrogen and form hydrogen halides, but fluorine reacts vigorously, and the typical reaction is when hydrogen and halogen this mixture is there. So in that mixture, hydrogen vigorously react with halogen and there is a formation of HX, that is HF, HCl, HBr and HI. Now reaction with hydrocarbon. Fluorine, it is the most reactive and therefore it decomposes hydrocarbon. So when it is mixed with methane, then there is a replacement, there is a actually breaking of bond between carbon and hydrogen. All the 4 bonds are broken. There is a formation of carbon and 4 hydrogen fluoride molecules. This is the decomposition reaction. So chlorine substitutes hydrogen from the methane and there is a formation of carbon tetrachloride. So this is the substitution reaction, whereas fluorine decomposes the hydrocarbon. Now reaction with alkali. Fluorine reacts spontaneously with alkali and form fluorides. For example, NaOH plus F2 gives sodium fluoride, oxygen and water. Other halogens react with cold NaOH and form halides and hypohalides. For example, chlorine reacts with cold sodium hydroxide and form sodium chloride and sodium hypochlorite. The sodium hypochlorite at higher concentration forms sodium chlorate. So chlorine reacts with hot concentrated NaOH and directly it forms sodium chlorate along with sodium chloride. Now bleaching action of the chlorine. Fluorine and iodine does not have a property of bleaching or no bleaching action. Chlorine is good bleaching agent, and the reason for this is when chlorine is mixed with water, there is a formation of hydrogen chloride and hypochlorous acid. This hypochlorous acid decompose and there is a formation of nascent oxygen, and this nascent oxygen, it is responsible for the bleaching property of the chlorine. So in this way, these are the some chemical properties of halogens. In addition to this, halogens undergoes displacement reactions also. Higher halogen displaces the lower halogen. For example, fluorine displaces other halogen. Okay.